So let's do this example. And this is a much more complicated example. This example is called a bridge, a Wheatstone bridge. And I'm going to give it to you entirely in the frequency domain, because by now you probably feel fully comfortable saying Z sub L is equal to J omega L and Z sub C is equal to 1 over J omega C. All right, the question says find I naught. And interestingly enough, if you find I naught, you can also find the equivalent impedance of this whole circuit, because the equivalent impedance of the whole circuit would be equal to the voltage source divided by the current that's flowing. So let's take a look at this. Is there anything that can be combined in series or parallel? And the answer is no. There's nothing that's in series. All the current through one device does not necessarily flow through here. Some of it, gets added or subtracted by this guy in the middle. Similarly, there's nothing that's in parallel. These guys are not in parallel. To be in parallel, you've got to be connected at the top and the bottom, and they're not connected at both. So we can't simplify this. Our method, though, is going to be clearly phasors, because I've written it in the phasor domain. So now the only choices that we've got to solve this thing are superposition. We could definitely use superposition. We could short this out and only have this thing going, and then open this and only have this going. So when we open this, we're making this a 0 amp source. Either way, that's still going to give us two pretty complicated circuits. So that's maybe not the smartest way to do it. Another way to look at it is to do nodal analysis. And we could definitely do nodal analysis. We could put a ground down here. We know what this node is. It's 60 angle 0. We don't know what this is. We don't know what this is. We don't know what this is. So we'd end up with a 3x3 set of equations. Definitely doable, but that's not the way we're going to do it. Instead, we're going to look at it by mesh. And the reason why I wanted to look at it by mesh is that we've already defined one of our mesh currents. We've already defined this as being our I naught. So I'm going to finish drawing that in. So this is our I naught. And we're drawing it going in that direction. At first blush, it looks like there's going to be 3 meshes, right? Except for the fact that we have this current source in the middle that's shared. So we have to get rid of that mesh and somehow create a super mesh whenever you've got a shared current source. And that super mesh cannot include that shared current source. So here's our other mesh that we're going to do. In fact, I'm going to draw that in a different color just to make it clear. And it's completely arbitrary what direction that we draw this current in, because I don't know what direction the current flows. But since we're drawing the current going down here from I naught, I'm going to draw the current going in the same direction for this I sub 1. And that way, when we're talking about the total current going through this capacitor or this resistor, it'll be I1 plus I naught rather than I1 minus I naught. And I'll save us just a couple of signs. We're going to start off by doing a KCL around our I naught loop. And let me start it by this minus sign. So we've got a minus 60. And you know what? 60 at an angle of 0 is just the same thing as 60. And that's because, remember, we've got our complex plane, we've got our real part, we've got our imaginary part. If we've got 60 at an angle of 0, that's going to be someplace that's 60 units away. This would be at J60. This is at positive 60. This is minus J60. This is minus 60 over here. And it's going to be at an angle of 0. So here's our angle of 0 degrees relative to our x-axis. And that just puts us at a real value of 60. So let's just write it as a real value of 60. So negative 60 plus the voltage across this 10 ohm resistor is going to be 10 times the current through it, which is just from our I naught mesh. And then we're going to add to it our minus J4. Over here, we've got 2 currents going through it. We've got our I naught and we've got our I1. So let me just address a question some undergraduates have, which is what current is going through this capacitor? We've drawn it as I naught over here. We've drawn this I1 over here. What gives? And the answer is that the true current going through here is both I naught and I1. I naught is just the partial current going through from this left mesh, and I1 is the partial current going through here from our right mesh. It's possible if you've got a really complicated mesh, if you've got something that looks like, here's a circuit fragment, part of a big thing with tons of meshes inside, and it's possible that you've got a circuit in which, if we call this simply, say, I1, that I1 does not flow through any of these wires here. Instead, you've got to figure out what the partial currents are from all the wires around it. And now this current here, the current through this wire here is going to be the sum or difference of these two. This is going to be the sum or difference between these two, and so on. So the true current that's going through, that's going down this capacitor is I naught plus I1. The true current going down this 5 ohm resistor is going to be also I naught plus I1, and that completes our circuit. So now let's rewrite this with our variables on our left and our constants on our right. The question is, how much I naught do we have? And the answer is, we've got 10 from this, plus 5 from this, that's 15, minus J4 from this. How much I sub 1 do we have? Let's see, we've got 5 over here. That's our only real amount. And we've got minus J4 over here. We've got no other variables, and we've got 60 that we can place to our right. That's our constant. So that's our first matrix equation. And when we write our matrix, those will be our coefficients. When we do our KVL around I sub 1, let's start arbitrarily right at the top. So we've got minus J4, and it's both I naught and I1 contributing to that one. Let's see, going down this 5, we've got also I naught and I1 contributing to that. Going up here through the J6, it's only going to be I1 contributing to that. And going up to J8, it's only the I1 contributing to that too. And all this has to be equal to 0. So now to simplify this, we say, how much I naught do we have? We usually write the real part first. So we've got 5 from here minus J4 from here. How much I1 do we have? Again, we usually write the real part first. We've got 5 from this. We've got a lot of imaginary parts. We've got minus J4, minus J6. We've got plus J8, and all that equals 0. So let's simplify this down again. We've got 5 minus J4 of I naught, and we've got 5 minus J4 minus J6 plus J8. That gives us minus J2. And so again, the matrix coefficients will be this for I naught and this for I2. So let's write that matrix. We've got 15 minus J4, 5 minus J4, 5 minus J4. So these two are these top two, and then these bottom two are going to be these bottom two, 5 minus J2. And all that is I naught and I1 equals 60 and 0. Placed in your calculator and solved, keeping it in degree mode and in complex polar mode gives you your I1, gives you your I0 and I1 equaling this. And so now we can write our I naught in polar form, polar phasor form. We cannot write it as a function of time because we don't know what the frequencies are. It'd be 5.95 times cosine of some unknown frequency times t plus 3.2 degrees. And all that is in amps. And there's our answer to a fairly complicated equation using supermeshes.